Our next speaker is Glen de Vos, the CTO of APTIV, and he will be talking about the role of AI in AV.
So good afternoon, everyone. So what I'm going to talk about is APTIV's perspective, or how we think about AI as it relates to automated driving. And I'm going to walk you through a little bit of, kind of maybe a historical context, and then talk about how we're implementing AI as part of our platform solution, and then why we are doing it the way we're doing it. So what's shown on the diagram here, and I won't go through this in detail, but this is the sensor configuration that's on our cars that are currently driving in Las Vegas. We announced here a couple weeks ago a commercial pilot with Lyft that'll have 30 vehicles doing point-to-point ride-hailing in Vegas. We have another 30 so there's about 60 cars riding in Lyft out of almost 100 vehicles that we have on the road today. So this is the sensor configuration. It is evolving, so if you're taking pictures, just know it, the next time I show it, it'll probably look differently. It's evolving, and that's because the technology is evolving. But there's one thing that's not, and that is as you think about level 3, 4, and 5, the car is in control. It has to manage safely all of the use cases that it encounters. And the simple ones are relatively simple to do. In fact, you can do, technical assistance. Excellent. So you can manage quite a few with a relatively simple setup, but to manage the full array of use cases, you really need a very sophisticated platform. Just a simple left turn, and this is taken from one of our cars in Singapore where we drive, where you see a number of different actors or agents around the vehicle, and not only do you have to correctly classify all of these agents, you have to actually understand what the intent of those agents are, how they are going to behave. So that as you pilot that vehicle down that street, that thing that we do without really even thinking about it, but the car has to do on its own, it's a tremendous amount of different combinations of possibilities that you basically have to comprehend and calculate. And even a simple left-hand turn can become an incredibly complex task. So to do that, you need AI, and there's no question about that. And in fact, AI is one of the enablers is really one of the major enablers for automated driving. You need perception, you need planning and policy, and you need controls, but AI underpins all of that. It allows you, as a very powerful tool, to manage that complexity, to actually incorporate. So AI has been around a long time. It's not new. There's a lot of things that fit under the AI umbrella. We talk about machine learning, deep learning, reference learning, unsupervised learning. All those things kind of make up the composition of AI. And it requires, as you probably heard earlier today, a massive amount of data and a large amount of computation. And that's been one of the biggest breakthroughs, is our ability to handle that data, and then the GPUs and the FPGAs that can actually do the computation. That's what's enabled a lot of these AI-driven systems. But what I would also tell you is AI as a tool has strengths, but it also has weaknesses, and those weaknesses need to be comprehended. When you use a tool, you have to be careful in how you apply it, and that's how we think about it. So what we've historically talked about in this approach to automated driving is two approaches. One on the left extreme is the rules-based, or where you write rules for every scenario. And that was the historic model for automated driving before these GPUs and AI could really be used. So you did incredibly complex algorithms that you would patch and try to adjust to accommodate every use case or every new edge case that you came across. AI, on the other hand, kind of approaches it completely differently, but they actually have something in common, and that's complexity. And they both basically result, when you think about an end-to-end AI or a fully rules-based system, they both result in incredibly complex systems that are extremely difficult to develop, to debug, and to manage. And all of that translates into you can't scale. And so one of the important things that everybody has to keep in mind about automated driving or these systems, it isn't sufficient to build one car that can drive around a block. You have to be thinking about how do you scale that platform to be able to drive millions of vehicles, different types of vehicles, different use cases, different environments, different cultures. You always need to be thinking about scaling. Pure end-to-end doesn't allow you to scale. Rules-based doesn't allow you to scale. And really, that complexity, if you think about both of these, that pure end-to-end AI and the pure rules-based, They're what we call generative systems. You take a bunch of inputs and you try to get a desired output. Complexity is the limitation. Computational complexity, all of the GPUs and performance you have to put in the car. Sample and model complexity, how do you make sure you have every single use case covered? When a neural net sees something it's never seen before and it doesn't know how to handle it, you can't predict its behavior. Debugging and verification along the way. How do you go back and fix something that is broken when you can't actually see it? And then updates and maintenance. How do you maintain this platform on an ongoing basis as sensors change, as the vehicle changes? As you put your platform into a new car that has a completely different control system or propulsion system, that affects the entire equation. How do you do that? So really, when you think about those approaches, it says you can't get there from here with either. You really need a different approach. And that's what we call structured AI. And what we mean by that is we take what we think are the best of both. We take the framework and the deterministic rules of the rules-based system, and then we combine that with the power of AI in being able to solve things that we simply cannot solve with deterministic rules. You can almost think of it, AI is, in my mind, it's an incredibly powerful curve-fitting tool. So for different types of problems, it's the only way to solve them. But I don't need AI to tell me what the speed limit is. And I don't need AI to tell me what the braking distance on a car that has 23,000 miles on it, has tire wear, brake pad wear. Those are things I can determine in a closed-form manner. So when I look at the problem, I say, I want to use AI where it makes sense. I want to use rules and deterministic methods where it doesn't. And that's really how we learn. If you think about, if any of you have been to driver's school or performance racing schools or advanced driver's education, the first thing they do is they don't put you in the car. You spend a significant amount of time learning about vehicle dynamics, braking distance, how the vehicle controls, rules of the road, all of those things. We teach that foundation of basic principles, which a 16-year-old can manage, and then we apply that to in-car driving experience. So it's the combination of the two. This is how we actually learn to drive. And this is why you don't have to get retrained when you go from one area to another. You have to get experience, but basically you don't have to retrain the system. You just you adapt and reapply. So we can tell the car, well, who can drive what, where, and when, at what speed, in which direction, who has the right of way, how to use and interpret active and passive signals, and where one can park and stop, and a whole host of other things. And it really isn't that complex. I don't need to write rules for every scenario. I need to write governing principles that basically provide a framework within which I can apply AI. And by doing that, it allows me then to scale that platform. I won't go through this entire slide as time doesn't permit, but fundamentally, it just reinforces we start with the basic principles of safe operation and the rules. Now, the point I'll make, it's not just about safety, it's about performance as well. Because you can have a very safe car that will make you sick. Driving in the back of that car will be a horrible experience because you're not optimizing performance. And for automated driving, it isn't good enough just to have a safe experience. You need to have a quality drive. You need to drive in a way that the passengers feel secure, they feel comfortable, they don't feel anxious or nauseous. And I think all of us have had the experience when we get in the car of an inexperienced driver or somebody who drives in a manner that is not exactly to our liking. It's a bad experience. And you can't solve safety and performance sequentially. You can't say, I'm going to come up with a really safe AD system, and then I'm going to work on performance. Because the two are completely combined. They're tied together very tightly. If you adjust something on the performance side, it impacts safety. And you have to make trade-offs. But the good news is those trade-offs are manageable. So how do we do it? So the first thing is, if you think about the automated driving platform, you can really break it down into three categories. It's the perception system, planning and decision making, and then there's what we call an AI arbitration layer. And some may call AI arbitration policy. There's a lot of titles for different things going around. But fundamentally, we use AI in the perception system, and this has been used for many, many years. This isn't new. You use AI for improved object classification, semantic understanding, building the model of the world around you. So AI is a very powerful tool for doing that. The next is the planning and decision-making system. And what that does is it generates all of the possible trajectories that the car can travel. So as it looks at its mission, and in our case, we break it down into short, medium, and long term. So we have basically three path planning horizons. Very short term, what's happening within the next half a second. Longer term, what's happening within the next 5 seconds, and then maybe 10 seconds beyond that. So you break that down and you look at all of the potential trajectories that the car can do based on what we think the agents around the car are going to do. Now, that can be done in a variety of ways. In fact, we could take anybody's planner and plug it into this platform. But essentially, we use AI to do that as well. So artificial intelligence is a really powerful tool for solving that, the left-hand turn question I showed on the other chart, and coming up with potential routes that the car can take. Different types of acceleration, lateral acceleration, different types of, basically braking, turning radius, all of those things, stopping or proceeding, all of those things that you really have to have as part of the path planning. And then the AI arbitration layer comes into play where it assesses those inside of that rules-based framework to solve for what is the optimal route. And what it's doing is it's looking at all of the different, basically, costs of the system or the rules and the significance that we put in, and basically saying, how do I solve that or optimize the path of the vehicle through solving for what we call minimum rule violation. Now, what's implicit there is we allow rules to be violated. For instance, depending on the situation, there's a double yellow line in the US, you're never supposed to cross that. But we all know that in certain situations, you have to. Otherwise, the car will never move. And so there's a whole host of trade-offs that have to be made that you can basically establish as part of a hierarchy or a prioritization of the rules. The AI arbitration layer essentially compares all of that and then optimizes for both safety as well as performance and looks at all of the different potential routes that you can have and then solves for the optimal route in that fashion. And what that allows you to do then is you can actually manage and predict what the car will do, and you can explain why it did it. And a key point here is when you think about some of the computational needs of creating path planning and looking at all the variables, the computational needs in those situations tend to expand as an exponent of the variables. When we think about this complexity, it's basically linear with the number of rules that you have. So it's actually fairly light on the computational side. And really what that reflects is it's extremely difficult to calculate perfect motion. But once you've calculated motion alternatives, it's actually fairly straightforward to pick the one that's best. And that's what this approach does. And that's what we're using today. And so, when we look around the landscape and we look at all of the people involved with automated driving and talking about automated driving, there's really no substitute for actually driving and driving at scale. 4 years ago, we were doing demos driving in CES around, probably a fixed route. Last year, we had progressed to where we were doing point-to-point drop-off service. And it's that kind of progression that actually allows you to really understand the limitations of these systems and how they work. And that's what's happening in Vegas today. As I mentioned earlier, with the 30 cars that we're putting on the road with Lyft, with our own development vehicles, and the roughly 100 cars or so that are driving around the world in Singapore, in Pittsburgh, in Boston, in California, as well as Vegas. And that gives us the chance to really stress test and validate this approach. So finally, when we talk about structured AI, why do we approach it this way? There's really three reasons. Because the current traditional, basically rules-based doesn't work. You can't get there from here. And end-to-end AI doesn't work. They don't scale. There's not transparency. You can't see inside the code. And basically, you can't have the confidence in those systems to get to where you need to be. Structured AI and the way we're doing it and the way we're approaching it gives you those things. It gives you a scalable platform that is transparent. And what I mean by transparent is I can explain to regulators, to OEMs, to the public how my system works and how it will behave. It isn't a matter of, it's not a neural net that's governing that exclusively. I have systems in place that allow me to explain that. And for those of us in the auto industry that have been in front of regulators, that have been in front of investigations with NHTSA, NTSB, other governing bodies, the answer that I really can't tell you how it works is not an answer. You have to be able to explain how these systems work, why they did what they did, and what you're doing to fix it. And that is fundamental. And there's no getting around that. There's no amount of testing that is going to get you around that issue. And in particular, with regard to liability laws. That is, you have to be able to say, I understand how my product will work in every environment. And this allows you to do that. Finally, it solves for both safety and quality. You need to solve for both at the same time, and this allows us to do that. So we can make those trade-offs. We can solve for, basically get the performance we need, but in a safe manner. And this, for us, this is absolutely paramount. So thank you for your time today. It was a pleasure to be here and talk to you about this. Perfect.